In the previous episode, we discussed Weber's generalization of Dirichlet's theorems. To Weber, this theorem is actually a statement about the generalized ideal class group. However, for a given number field K, this theorem only holds for ideal group H of K, for which there exists a finite Galois extension L over K, such that H is basically the set of all K primes splitting in L, with finitely many exceptions. Now, such an L is called a class field for H over K. If H is an ideal group of modulus M, then we define the class field for H over K to be the finite Galois extension of K such that for all the primes P not dividing the modulus of H, P splits over L if and only if P lies in H. Now, notice that we said the class field of H over K, not a class field of H over K. And that's because class fields are unique if they exist. So why is that? Well, this is due to the theorem by Bauer that we have discussed before. Recall that finite Galois extensions of a number field K are uniquely determined by the set of K primes splitting in them. Thus, if an ideal group of a number field K has a class field, then the class field must be unique. Of course, the next natural question is, do class fields always exist? But before we answer that, let us first look at some examples of class fields. For our examples, let's take K to be Q. First, let us find the class field corresponding to the ideal group with modulus 4z. Recall that this ideal group is defined as follows. It consists of fractional ideals generated by A over B, where A and B are integers such that A is congruent to B modulo 4 and A over B is positive. Now, to find a class field for this ideal group means that we want to find a Galois extension L of Q such that for every odd prime P, P splits over L if and only if P is congruent to 1 modulo 4. Now, if you have taken an algebraic number theory course, then you know that the rational primes splitting inside Qi are exactly the primes that are congruent to 1 modulo 4. And thus, the class field of the ideal group corresponding to the ideal 4z is exactly Q adjoining I. Similarly, since the primes splitting in Q adjoining square root of 2 are just those that are congruent to plus or minus 1 mod 8, we have that Q adjoining square root of 2 must be the class field of the ideal group corresponding to the modulus 8, as well as its negative, since they are generated by elements of Q that are congruent to plus or minus 1 modulo 8. So those are some examples of class fields. Now, let's come back to our questions. Do class fields always exist? Well, Hilbert conjectured that they do when M is 1 and H is just P plus of M. The corresponding class field in that case is nowadays called the Hilbert class field. Now, Hilbert was drawn to this because of his interest in unramified extensions. Remember, the key in Hilbert's proof of Kronecker-Weber was that Q has no non-trivial unramified extension. Now, another reason for Hilbert's interest in unramified extension was in his difficulty with proving his product formula. Hilbert wanted to generalize quadratic reciprocities for number fields, and thus he defined a new symbol, Hilbert's symbol, generalizing the Legendre symbol. He then proved the following product formula, which implies quadratic reciprocity. However, his proof breaks down for number fields that admits an unramified quadratic extension. So he became very interested in studying unramified extensions. Now, drawing on an analogy between number fields and Riemann surfaces, Hilbert made the following conjecture about the existence of the so-called Hilbert class field. The Hilbert class field of a number field K is the maximal unramified abelian extension of K. Its Galois group turns out to be isomorphic to the ideal class group of K. And every ideal of K becomes principal in this Hilbert class field. Moreover, for every k prime p, the inertia degree of p is equal to the order of p in this ideal class group. In particular, observe that p splits completely in this Hilbert class field if and only if the inertia degree of p is 1, and that's the same thing as saying that the order of p is 1 in here, i.e. p lies inside p1 plus. In other words, the Hilbert class field of K is just the class field corresponding to this ideal group. Now, Hilbert made this conjecture and was able to prove part of it. And then Wrangler was able to extend this proof. But it was the Japanese mathematician Takagi who finally managed to prove existence of Hilbert's class field in full generality. And that's what we are going to discuss in the next episode.